So I've had quite a few people asking how to set up the device, how to set up a gpvdm device, and how you set up the optical simulations, how you set up the electrical simulations. So the first thing, so I thought I'd make a video on this. So the first thing is worth noting is that there's two distinct types of simulation happening within the model. There's an optical simulation and there's an electrical simulation, and they're basically split. They're two sets of equations that you solve separately. So I'm first going to talk about setting up the optical simulation. So here's our device structure. All layers in this device, so the ITO, P-dot, P3HT, aluminium, are all part of the optical simulation. So light comes in from the top, and it's all these layers are simulated optically. We can set up this optical layer structure by looking at the layer editor, and there's three columns to this. There's this layer name, thickness, and optical material. This layer name is literally just a nickname for the layer, so you can set this to anything you want. It doesn't matter. And it's just so you know what the layer is. You said ITO or whatever. Next we have the thickness, so we can set the thickness here. It's in meters, so we can change this to 100 nanometers, hit return, and that's done. The final column, optical material, here is effectively the optical material you're using to simulate the propagation of photons within the device. So you can select a new one just by highlighting a row and then selecting whatever material you want from the materials database, and and popping it in there. So I could pop in this material here, and it would swap out the refractive and optical indices for the new material. The final column, and then I'll come on to the final column in a bit. So if we just click simulations, optical simulation, if we run a simulation, it's now calculated effectively the photon profile within the device, so we can look at the photon, where the photons are absorbed as a function of position and wavelength. 0 here is the start of the active layer, something I'll talk about in a moment. This is the photon distribution within the device, and this is sort of a 1D plot of what's going on. You can change the illumination, so you can have an LED, a xenon light, whatever you want. You can pick a particular wavelength to look at. So here we're looking at all the wavelengths, and now we're looking at now that should be 360. I think it's just failed to update, but that should be about 360 nanometers. So that's that. That's effectively the optical simulation device. Now I'll keep this up just to have a, there we go. Now there's one layer in the device which is called the active layer, and this is the layer in which not only the optical equations are solved but also the electrical equations. If you think about a solar cell, very often many of the layers, or what's going on in many of the layers, electrically isn't really that interesting. So for example, the ITO, well, it's a conducting sheet. It's probably not worth simulating all the electrical equations over. The same with the P.dot PSS, it's sort of a conducting sheet, not that exciting. It's just, we can probably just model it with a resistance. There's no point in solving all the electrical equations over that sheet. And the same with the aluminium, it's just a bit of metal, not that interesting. We can just we don't need to bother solving electrical equations over it. So what we do, to sort of save computational time and save time setting up the model, what we do is we say, let's just simulate one layer electrically. So that's this P3HT PCBM layer we're going to say simulate electrically. And so on this layer type column, I've got contact, 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 and this just means these are contact layers. I'm not that interested in them electrically, so don't bother simulating them electrically. On this layer, however, I set it to the active layer, which means let's bother solving electrical equations over that layer. You can have more than one active layer, so you can set this one also, the P.dot, to also be an active layer, and this would then mean, it'll update in a second, and you see you now get a little blue bar on both the P.dot PSS and the P3HT PCBM. This just says that we're now interested in both these layers electrically, but I really suggest you keep it to one active layer in your device, unless really you've got some sort of exceptional circumstance you're interested in, because you can really simulate most things with just one active layer in my experience. Whoops, there we go. In my experience, so you can simulate almost all solar cells with just one active layer. So once we've set up our active layer and decided which are our electrically interesting layer, we can go to electrical parameters, and if you go to electrical parameters here, these are the electrical parameters that describe how that layer performs electrically. So we've got electron mobility here, hole mobility, so again everything's in meters, relative permittivity, number of trap states, density of trap states here, and this is the tail energy of the trap states. So if you look up Shockley-Reed-Hall theory, it'll tell you all about sort of how this trap state works. I might make another video on that if you request it. These are the trapping cross sections. So the free electron to trapped electron cross section, trapped electron to free hole cross section, trapped hole to free electron, and free hole to trapped hole. There's only 4 of them. Again, this is all part of the Shockley-Reed-Hall model, which if I get requests to make a video on it, I might do that. Here we've got the band gap and the free electron to free hole recombination rate. So if we go ahead and simulate a simulation, let's get rid of that, and plot the results here. So I'll press G to get a grid. So here's 0. We've got a VOC of just over 0.8 volts and a JSC of about 150. So if now, for example, I change these parameters, so let's bump the mobility up by 4 orders of magnitude. Let's reduce the tail states to something really short to reduce trapping, so 30, reduce the number of trap states here, say. So I'm just trying to make it radically different so we can see a change. Yeah, okay, and then if we rerun this, we should see a change in the JV curve. So we've got JSC at the moment of minus 150 and VOC of 0.8. So if we refresh this by pressing A and then zoom back in and press the grid, it's not actually changed all that much. Oh yeah, so VOC has actually gone down a little bit, so down to about 0.8. It was above 0.8 before. So effectively, if you have experimental data and you want to fit your model electrically to it, you can change these parameters in effect to shift this JV curve around to fit your experimental data. But you obviously want to make sure you've got your right layer structure. Oops, where's the layer structure? Layer structure in there before you start doing that. That's really it. That sort of describes how devices split up electrically and optically, I guess. So I think that's it. So thanks very much.